Fatigue failures often occur at welded connections. On the left, you can see a failure at the connection of the flange in the pipe. The photo shows a longitudinal crack at the toe of the weld. On the right is another type of failure. This failure is due to lack of fusion. The photo particularly illustrates that it is very important that the welder is qualified and is capable of providing sufficient fusion of the weld material. So there are different types of crack failures. The first is a transverse crack, which is a crack in the longitudinal direction of the weld. Second is a toe crack, which is a crack initiated at the toe of the weld through the base shell. The third is an underbead crack, which is a crack on the rim of the underbead and the base shell. And the fourth and final is a root crack, which is a crack initiated at the root of the weld. And this is the most important crack that could be caused by the lack of fusion. Before moving over to fatigue, it is important to assess the static strength of the weld. The weld strength capacity depends on the weld pattern, throat size, and the weld material. The manual calculation procedure is as follows. Step 1 is the calculation of pattern properties, which are the areas and the moments of inertia. Step 2 is the calculation of the shear, F2 and F3, and the axial, F1, forces, based on the global forces, moments, and the weld properties. In step 3, we calculate the resultant force, Fw, and finally in step 4, we compare the force, Fw, with the allowable shear force of the weld material. In both static and fatigue analysis, it is important to estimate the throat and inertia properties. These properties depend on the different type of welds and pressure vessels. The most important weld types that we encounter are the full penetration weld, the partial penetration weld, and the fillet weld. Based on the type of weld, the weld throat and root penetration differ significantly. In static design of pressure vessels, in both the ASME Section 8 Division 1 and the ASME B31 codes, the joint efficiency property is used. The joint efficiency is defined as the strength of the weld with respect to the strength of the parent metal. For a weld as good as the parent metal, the joint efficiency factor E is equal to 1. For a weld weaker than the parent metal, the joint efficiency factor E is less than 1. The joint efficiency depends on the weld type and the degree of radiographic inspection. Within the ASME Boiling Pressure Vessel Code Section 8 Division 1, Table UW12 provides an overview of the most relevant joint efficiency values. It must be noted that the joint efficiency must be used for governing welds only.